So good night, everyone. So today I first introduce what we will discuss today. So first, because in stage three, all the lecture is mainly help you for finish the stage three project. So stage three is also I have seen that in stage two, you already used to that when you write report, you already emphasize which member contribute which part. So I think this is the same for the three. You know, stage three have a high percentage uh, for this subject, but the most students I should say after stage one and two nearly pass, or some already pass. But in that case, stage three is mainly I know some students they aim for DHD and even more, so we need to uh, uh, do best. And today I want to see because we have several topics we need to cover to help you to finish the stage three. So the first is like modeling. Uh, Modeling include static uh, modeling and dynamic modeling. So this is normally we after filtering, you use signal analysis or signal pre-processing, and then the next step is one is modeling. And this one project will use modeling skill. The other one, I think, is uh, classification. So we will discuss classification maybe next week for next week. And then we discuss 2D image processing. This 2D image processing maybe you will not be used in the project, but sometimes, for example, they use image processing to do for example, if you have a single signal, like for example, your EMG signal or EEG signal, you can do wavelet or short-term Fourier transform, and then your single this 1D signal, right? This only 1D signal. So 1D signal normally is you not need to use signal processing, but if you use FFT, short-term Fourier transform or wavelet, you can change as a 2D signal, and then you can use 2D signal processing and to take the features. And I will discuss about the fundamental, for example, how to do uh, uh, or do the uh, Fourier analysis and for 2D signal, and also how to design a filter like low pass, high pass filter to do the processing for 2D signal, and even 3D signal. I also use the example to talking about 3D signal as well. So for medical image and medical 3D image is very important part. So we need to be uh, very uh, careful for this. In the future, maybe you will let, although for the project, maybe you no need to worry about. So that's why I will include the 2D, 3D, and the last one is control. And this one is maybe you will use, but it's not very likely. But for example, today I discussed for when you do exercise, how to control your exercise intensity to guarantee your body in the safe range, especially for old people. You know, like if some patient if you do rehabilitation, so they need to control the exercise intensity. So they need to use for some control algorithm to like guarantee your control. For example, you want to maintain your heart rate in the safe range. For example, 80% of your maximum heart rate. So that's kind of there's lots of things we use control, but I will discuss that control later if we have time. Now we look at I share the screen and to look at what I have put in the so if I go to so this is our I already published the lecture 7 and lecture 8. So we look at lecture 7. So if you open this one, lecture 6. So this module 3 include lecture 6. So I should say week 6 is not necessarily week 6. So it's like week 6 maybe have sometimes week 5 we have 2 lectures. So we just based on lecture 6. This lecture 6 is for biomedical signal, biomedical system modeling. So before I go that, I want to go to the modeling. I want to get some connection because we already learned signal processing, but this signal processing, one is use uh, FIR. This is mainly linear time invariant filter technique. So there are different equations, and another one is we use wavelet and also short time Fourier transform. Although like denoise use wavelet is kind of little different with FIR filter, but fundamentally they are still linear filtering. And then also, of course, you can use nonlinear technique and then, for example, thresholding, and maybe make it nonlinear. But the fundamental, it still belongs to linear filtering. So that's my understanding. Maybe not fully. Sometimes it's not fully accurate, fully correct. Because if you use a nonlinear technique, and then they will be nonlinear. And one thing I want to emphasize: all this kind of filtering technique we learned is basically is a frequency based. Even for the wavelet, actually they also have frequency. Do you still remember we have wavelet? We have a center frequency as well. So it's still they thinking about because frequency and the scalar they have some relationship. Although they are inverse, but they have some connections. So in the future, if you continue to learn signal processing, I still want to discuss some other kind of signal processing technique I want to discuss with you. The first one is, do you remember in sometimes we uh, put a random noise into the signal, and then the random noise actually is not frequency based. Because the random noise they means like they have every frequency signal noise in theirs. They means pollute the signal. So if you use the FIR, IR, or even wavelet, it cannot totally you can get rid of this kind of signal noise. So this they have another kind of I think filtering method. If I go to uh, go to assignment 3. So for example, called stochastic filtering. So stochastic for filtering, like this one is they put a noise. This noise is random noise. So it's they are not necessarily related with frequency. For this kind of things, you need to use, for example, some technique, one called Bayesian, Bayesian network or Bayesian based called posterior uh, estimation. They want to give you a noise polluted signal. Can you based on the noise based noise polluted signal, and then you use some prediction, and then you get rid of the influence of the noise. So one of the most famous one you may be heard about is actually uh, called the Kalman filter. So I'm not sure you have heard about the Kalman filter. So Kalman filter is very popular. This one is a kind of if I use so Kalman filter is a kind of stochastic. So it's a kind of stochastic method. So we look at this is a Kalman filter. Kalman filter is mainly for linear system. So today that's why I want to discuss about modeling as well. So if you have a model, and then normally you can use model to do prediction, and you also have measurement. For example, this is for the linear. This is a linear case, so linear model. I'm not sure you know about state space model. If you have learned some basic linear theory, so you know linear theory, we both normally we use difference equation or differential equation to describe a system, but we can also use a group of differential equation or group of difference equation to describe system. So use group of difference or differential equation. Normally it's first order difference or differential equation. They can describe the system. This is called state space model. So state space model, for example, here you can see the noise is enter to the system. So this is a noise. So here is if you use this normal distribution or Gaussian distribution noise, the zero mean is called white noise. So white noise, and then based on these two, this is a model, right? If you have this model, and then this is the states information. So the updation the states. So if you have this model, you can even you don't have measurement, you don't have measurement. If you know previous states, you can use this model to predict next states. So this is called state prediction, but this is use model. So today we will discuss how to model a system. So if your model is very accurate, and then this noise, this is called modeling noise, this one will be very small. But if your modeling method is not good, then your modeling error will be not good, will be big. So if you use model to predict, that will be very uh, inaccurate. So in that case, you have measurement as well. So this is a measurement. So measurement, normally if you, for example, you want to estimate the room temperature, you need to have a temperature sensor. And then this temperature sensor is related with, this is called states. So this states may be not only just with temperature you are interested, maybe you are interested with voltage, interested with humidity, and this is all called states of the system. And then, but you only can measure temperature. But temperature will be influenced by other parameter and also by input. The input maybe is the air conditioning power. So, so that's the things. You measure, when you measure, you still have noise. So in that case, you need to balance uh, between the measurement noise and the system model noise, and then you find the optimal weight. For example, if the model is very accurate, and then if it's 100 accurate, you don't need the measurement. So you directly use model to predict the next output. But not always the case. Your model always have error. So in that case, you only can give some, for example, 90%. We believe the model, and another 10% we believe the measurement. So Kalman filter is kind of based on this kind of uh, logic, and then they developed the filter. So they are mainly called stochastic filtering. Stochastic filtering is not, they are not from the frequency point of view to do the estimation, to do the filter the noise. So and also we have a lot of other filter method. For example, you have heard about median filter. Actually, median filter in MATLAB is we have median filter. If I search, maybe go to here, median, median filter. If you median filter, use MATLAB. So they have 1D, 2D, 3D. They have even 3D median filter. I will show you like how to do the filtering in 3D. Yeah, 3D median filter. So this is a non-filtered. So this is a non-filtered signal, right? But you can see there's lots of noise, 3D. But after you use this called this one, you can see median filter. And the median filter, after median filter, you can see quite smooth. So no matter it's 2D, 3D, or 1D, so it's very powerful. I mean, I show you one. I think I have one. Yeah, this is 3D in filter one. I can run this one. I implemented this one. So this 3D in 3D median filter. So median filter you can see is powerful, but it's very simple. This just you don't need learn any frequency analysis, no need to learn FFT, no need to learn wavelet. You just use a very simple logic. So what's the logic is like this. For example, you uh, maybe I run one of the data. If I run this one, so for example, this is the this is by measure the VO2 is called oxygen consumption during exercise. This is treadmill exercise. First, I'm not doing anything. I just like run. I'm just rest for a while, and then my VO2 is in the baseline. Is something like this, and then I working at 3 kilometers per hour. I working here, and then my oxygen consumption increased to a level. But you can see this is very noisy. This signal is very noisy. This maybe it's not frequency related, but you can use frequency. Maybe related with you can get rid of some frequency noise. And then when I running, because when you are working at 8 kilometers per hour, you cannot working, you must running. So you run, and then your oxygen consumption increased dramatically. And then when you back when you back to three, you are working, and then your oxygen consumption dropped as well. So in this case, how to get rid of this noise? This one called median filter. So median filter, we show you what's median filter. If we can call here, so this is the median filter. So median filter is here. I put here. So we know that we have output, right? So we have a YCP. But you know that this one is not very clean. So I use a filter. You have Y filtered, and I use Y filter. Maybe I just YF make it simple. So it's like I can use median. This is not 3D, so it's median 1D. So I just maybe I mean I can't remember what's 1D. Uh, so this is only one here, and then this times n. I will explain what n means, and maybe you already use this one, but I just quickly explain for you. So this one I put this is a signal, right? I want to put, for example, I put one. This is for the 1D one, and then the n is how many for example, how many simple we consider. So median filter means like you, for example, if this is 5, or maybe I make it 20. 20, that means when you pick the current value, you look at previous 10 and the next 10, and you find the median value. I mean, median value means like, for example, you have a 20 you have 20 sample. The median one is the number 10 or 11. So is that you order the sequence value, the sample value, and you find the number 10 or number 11, and then you use that value. After this, we can see what we can get, and I plot. If I plot YF, maybe we can see the signal become much clean. And if we look at, so with so you can see this signal becomes cleaner. So it's not that so much noise. But this one is very simple. It's just like, for example, for here, I just look at first 10 and the last 10, and I will find the median value. That means number. If, for example, if I put normally if you want to more smooth, you can just like simply put this to, for example, if you want to 50, and then there will be more smooth. But the problem is, well, you will damage some dynamic as well. So if you plot and will be more smooth, you can see much smoother, right? But you will have some damage some dynamics. So some is noise, some is dynamics. So this is, I give you a very a brief introduction. You still have lots of choice for the filtering, for the signal processing. It's not just like we teach. Sometimes the filtering is based on the noise property. If noise is not related with the frequency, you use the method before, stage one, stage two will not help too much. But unfortunately, most of the cases, the noise is related with frequency. So this is a statistic filtering, and also have some other nonlinear filtering method. Maybe you have learned about the Hilbert-Huang method or some other method. They are for nonlinear filtering. Uh, so our nonlinear signal analysis. So I will not go too deep to there.
Stephen,
Hi.
your microphone is having a problem, I think, because sometimes your voice is.
Oh, sorry. Now it's okay.
Yeah, now it's better. I think
Yeah.
you must be hitting your.
Maybe my shirt.
Yeah.
Okay. Yeah. So that is maybe I close to the microphone will be better. Yeah. 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 I close to the microphone. So
That's
today,
better. Yeah.
yeah, another very important signal processing method is actually called modeling. So why is this important? Because if you have a system, right, you get a signal. If this signal is the output of a system, if you know the system, for example, if you know the system model, and then you simply use the input, any input, you put this model, you can generate an output, and then this output will be with noise free. So this is called modeling-based uh, filtering. So I will show you. There's lots of paper. Actually, recently we developed electronic nose. When we because electronic nose is actually is there's a lot of gas sensor. You know, gas sensor when you cooking, if you have some fire or some smoke, and then the gas alarm will alarm, right? For electric nose, we use maybe 10 gas sensors. We can determine what kind of gas it is. So in that case, first the input is still very noisy. So the gas response, the sensor output of the to some gas or to some odor is also uh, very noisy. So we use a modeling method. Because when we use a normal signal processing method, it doesn't get good result. But when we use modeling method, it gets very good result. So I show you this. I'm not showing you my paper, but I show recently there's some other. I think I found a paper. Yeah, this paper. Oh, it's not this paper. Uh, Sorry, I cannot. Maybe I will show you this paper I put in the system later. But this paper I remember I read today. I think, yeah. Maybe. Sorry. Later I will show you. Because the time is very tight. But yes, there's another method. It's modeling based. So modeling based method is very sometimes very recently developed method. It's very new. But the idea actually is they use very earlier. And also for model based method also can in the future next stage we will talking about classification. You know, classification, the most important thing is you need to find the feature to do the classification. So the feature extraction is very important. Sometimes modeling can be used as a feature. For example, if you use a second order model and then you have three parameters, you can use these three parameters as the feature. So and then that's why today I want to emphasize is like modeling is very important. You know, modeling actually classical modeling is used. For example, you maybe heard about first order system and model this first order system. And also you heard about least square method. Least square is like if you have some point you want to find for example a straight line and to approximate the relationship, for example um, uh, between the input and output. So they for example, if you have a temperature sensor, your input is temperature and the output is the voltage. So if you want to find the relationship, for example, linear relationship, you can use least square method. Uh, but least square method, the general one, is for static system modeling. Now we look at maybe you look at our today's lecture, and today's lecture notes here. So this modeling. So modeling, I have put three video let you to read. So the first one is dynamic modeling. Dynamic modeling is very important. Why is it called dynamic? One is called static. Dynamic means like this system is can have memory. So they have states inside. So they can memorize what you have give the input before. But for the static one, the second one is called static modeling. That means this kind of modeling is like they don't have a relationship with the history. It's just like you give any input, my output immediately change to corresponding to the input. So this kind of system called static input. So there's two very important modeling technique we need to learn. One is for linear dynamic modeling. For nonlinear dynamic model is too hard. So it's no method, no good method to do the modeling. But for linear time invariant system, the modeling is very mature. I will introduce you MATLAB called System Identification Toolbox. I will show you use MATLAB to show you why, and then I will show you how to do the uh, dynamic modeling. So mainly it's linear for linear time invariant system. Uh, Maybe you haven't learned about the system before, but if you are in the, I mean, postgraduate or you are in the third year, maybe you know the first order, second order system. I assume you know that. And if you have a problem, and then you no need to select the project related with this technique. So I will later I will introduce uh, at least six projects, and your group can discuss which one you are confident to select uh, the project. So a project maybe all class select the same, doesn't matter. So they will have competition. But if you use different one, if you use different project, you select different projects. we are also support the resources to help you. So the first one is the one I want to introduce is to estimate the cardiorespiratory response to exercise. For this, I have do a long time research in this area because like Google Watch or things. Uh, we did the work similar as Google Watch to estimate the uh, uh, exercise intensity or exercise energy expenditure long earlier than a long time ago, maybe 20 years ago or 15 years ago. Actually, we have developed lots of model and things. The first project is related how to we provide you the data. So we use the gas analyzer, like when do exercise. This called K4B2. It's a K4B2. So they have some gas analyzer. They can measure not only just like oxygen consumption, they can measure carbon dioxide, can measure lots of things. So this we will provide you all the data when you do exercise to treadmill exercise, and then you just need to model the system. So this is when you do exercise, you want to know how much energy. So this
Så
one
du
can
la ut et
measure
bilde
your
på
heart rate
Instagram
and
der du
all lots
sprang
of
med en
physiological
maske
signals.
og
So
noe
this
apparat
one,
på ryggen. Hva var det?
the main thing is the good thing is like also for athletes, it's very important like uh, called oxygen VO2 max, called oxygen consumption max. That means like what's your exercise ability. So if you are good athlete, you should have very high VCO2 max. So we currently want to, for example, this VO2 max measurement is very difficult because you need to use K4B2. Number one, K4B2 is quite expensive. Number two, you are not comfortable when you do exercise. So if you in a real competition, you don't want to wear a mask, and this is very uncomfortable. So we want to use a wearable sensor, for example, accelerometer. We use a heart rate monitor, and then we can estimate your oxygen consumption rate. So this is what we done. So for this project, I will introduce later. Is like we give you the input. Is like because we know when you do treadmill exercise, we know your exercise speed change, and then we want to give you this one. You can model the system. So how to do the modeling? I will show you how to do the modeling, and with this one. This is mainly related with the first project. So the first one is first order system.
In this module, we will begin what we call time response analysis. So far in this
So for example, this is the step response. Like you give a step input. So for example, when you do the treadmill exercise, before you are for example running at walking at 3 kilometers per hour, and then this is one input is one the lower step input, and suddenly you change to 8 kilometers per hour, and then your running speed increase. This like a step input. Also for training athletes, the most important, the most powerful, popular one is called interval training. So they find the two level of exercise. They switch between these two exercise level, and then they can increase your VO2 max. But if how to change, how quick, how fast you change, you need to know the person's response time. So for different person, the response time is different. So some athletes is very response very fast. So when that means they are very fit and they are very fast adaptator. But for some exercises, they mainly want to they not necessarily fast, but they want to be last longer. So they can slowly go up and to a steady state. So this is what we want to learn. But for this one is modeling. For example, we not worry about this for isolate training, or we want to estimate the room temperature, or any mechanical system, electrical system, or even physiological system. We no need to worry. We just like treat it as a modeling. We just want to use a model to describe the system. So this is talking about this. So you remember, if it's a first order system, your response, I think you know that.
Understanding these standard sort of absolute initial conditions.
So this
and
is
then
first
we
order
rearrange it
system.
Further looking at this.
So this is the first order system. I hope you have touched this kind of system before. So this actually, you can see, YT is output, UT is input. If you describe a dynamic system, this is a dynamic system because this have a dot. Dot is differential with time. So this is a first order. So it's only first differential. So actually this is a first order system, but it's linear system. So this this differential equation you can solve easily. So you can use Laplace transform, and then you inverse Laplace transform. You can get solve this differential equation. So this, and also this is the first order differential equation. So for this one, if you want to model this system, it's very easy, right? If you know two parameters, and then this system is you can model. So for system modeling, the first important thing is you need to determine the structure. You need to determine the structure of this model. So the structure of this model is, for example, the order. First, you need to determine use linear, nonlinear, time invariant, or time variant. So normally, the easy to get the model, to identify the model, and also more robust the model. If you use very complex model, it will be training will be take time, and also and it will be sometimes accurate, but have problems like overfit. So that means the system is not the model is not robust. So for this first order system, this is a very simple model, right? You only need to determine two parameters. One is the steady state gain called K. Another is tau. Tau is time time constant. So this one is also low pass filter. You remember this is low pass filter, first order low pass filter. If you do the body plot for this one, so this tau is 1 over tau is a corner frequency, is a minus 3 dB frequency. So this first order, in that case, how to identify this model? Actually, this is first order is quite easy. If you do a step response, you can find 63% of the final value, and then that corresponding part is the tau. And then steady state gain is very easy to calculate. Is final value of output minus final value of initial value of output divided by final value of input minus initial value of input. So this is quite easy. So I don't discuss
transfer function.
You
in
look
order
at
time constant, many real systems
this
can be
time
well
constant,
approximated by a first
DC
order
gain,
model.
or DC.
Perhaps
So this is
the
an
most
example. Electrical
well-known example of a first order
RC
system is an
circuit.
RC to R times and some
And
resistance.
then this is the
For
temperature
example, you can
system.
imagine that the water itself has some
Thermal
thermal
system.
capacity.
So this is
The water is
also
able to hold
first
some
order.
amount. Other analogous system,
So this is
spring,
a tank.
it would also be modeled
mean
by a
tank,
first order differential
tank
equation.
system. And this is
So
mechanical
this is just
system.
a few
So they are
examples of.
all used first order. So first order is very
So looking at this,
commonly used.
if this expansive
So the
Laplace
step, this
transform
is step
table,
step input.
this do that is once we split it,
This
we
is
basically do the opposite and put
Laplace
it back
inverse
together by
transform.
getting a common denominator.
Do the
So in order to get a common denominator,
fraction.
plus b,
I
but in
hope
reality,
you still remember this, so they can calculate Laplace
and we
inverse,
get
and then they can
t
get
is this
what they want to get. This is the output. So this is the output
exponentially.
in time domain. So here is what
So
I'm
if I
talking
apply a
about.
constant,
So in that case, for the first order system, what do you want to know is two parameters. One is tau. Tau is time constant. How to find it? one method is you just directly draw a tangent line, and if cross to the final value, and then the corresponding part is the top. So what time it is now? Also, with time is very tight, and then when you another method is 63%, and then this part is 1 tau as well. So tau is easy to find, and then static again.
An input, which we have in this case a step.
So this is static
in
again.
steady state, this is how much the output will be multiplied. K is the it only approaches the final value, and since this
so I hope
being given the output response and
time,
trying to back out
read
the model
video.
instead.
And because if you select the first project, and actually this one you only need to use first order. The one I already draw here. I think if you look at the original figure. So I will give you this data, and then you need to find. For here, there's one step, but this step you can neglect. I'm only interested with what's the time constant here and what's the gain here. So in that case, you have step from here to here, right? So it's a step response. So it's a first order. You can use just any order you can use, but I think maybe first order is okay. And also I want to calculate this is called onset of exercise. So onset exercise normally, if for healthy or if a strong person, normally called onset exercise is quicker. So the time constant is small. But when the recovery, so when you from high intensity to low intensity, and then your body will recover. So this time will take longer. So this one take longer. So this is an example, but I will give you maybe 1 or 2 data, and you just do. First, you need filtering, and then you need to find the time constant and gain. So you compare with the onset and offset of exercise. We also not only just give you this, we have a heart rate, we have a VCO2, we have a ventilation signal, and we have a breath frequency signal. We have lots of signal. I will show you. I have some data. So this is a K4B2 project. I think. So this is the one data I show you. So this is a lot of you can see you have a time. This is a timeline. This is a RF, VT, VE, ventilation, VO2, VCO2. This all important data we recorded use K4B2. So we go all the data, and then you do analysis. Not only just like VO2, VCO2, you can also find the relationship between heart rate and VO2, and then you can use heart rate as input, VO2 as output. You do all the analysis. So this is the first project. You may need the technique for modeling. So this is a static modeling. Dynamic model, first order. You can have third order or second order. But another part I put here. Is a dynamic static modeling.
Hello and welcome to the screencast on polynomial to quote.
So this one is use polynomial. You know, like a polynomial can approximate the nonlinear relationship. Before I talk about you use least square method, right? You can find the linear relationship between input and output. But if the output and input is nonlinear, they cannot use a straight line to approximate. And then you can use a polynomial. The polynomial is, for example, you use quadratic, you use a cubic, and then this is a cubic model. And MATLAB is very powerful. You can directly call a toolbox. But the only thing is this one is cannot be used for the modeling of the one I just show you this one, because this is dynamic modeling. the dynamic. But this one is like your input should be, for example, if you want to use this method, it's something like this. For example, you want to find the steady state relationship between your running speed and then your VO2. So how to do that? You need to run at, for example, 3 kilometers per hour. For example, run about 10 minutes, and then your VO2 will be stabilized, and then you get 1 point. That means one is the running speed, another is the VO2, steady state VO2, and then you change the speed to another. You running to another speed, and you got after get steady state, you have a steady state VO2 as well. So you neglect the dynamic, and then you can use the polynomial, this one, to build the relationship. So for this one, maybe for the first project, you no need to use static modeling. But I have put 2 papers we read before. We even use more complex static for static modeling. And also in the other project, maybe you need to use polynomial regression. So polynomial regression, for example, someone use a EMG control motor or control a LED, and then you need to find the relationship between for example, the magnitude of envelope and also the strength, and then you can use a nonlinear relationship. Maybe linear one is okay, but maybe nonlinear is more suitable. So that's why I introduce static modeling as well. So actually, dynamic modeling, their modeling, and another, I will teach you how to use MATLAB to do that. Actually, MATLAB is based on the dynamic modeling is based on the static modeling method. They transfer dynamic modeling to a dynamic modeling method. But this one will be very complex. I will not introduce for this subject. But I want you to use the toolbox again, the MATLAB toolbox. They have system identification toolbox. Before I ask you, you use the 63% to model, but that is not the case, because if too much noise, you cannot find 63%. So the last one is very important, is this one. I want to introduce the called ident toolbox, system identification toolbox. So now maybe you need to concentrate on here, and I will introduce this one. If you select the first project, so I record this one.